Hello everybody. In this video I will talk about the hydrostatic forces and especially the hydrostatic forces on the vertical surfaces, and in the next video I will talk about the hydrostatic forces on inclined and the curved surfaces. So let me actually define what the hydrostatic forces are, and let's derive the relationships also. Alright, so what we do know, and again let me show you over here. So this is our wall, and this is the liquid. As from previous lectures, we do know that the pressure inside a fluid basically, or in a liquid, increases as we go down in the fluid, and the relationship how the pressure is increased is given by this rho gh, or gamma times h. So the deeper you will go inside the fluid, the higher the pressure would be. So I can make this as my coordinate system, which is y. So the more I go inside the liquid, it will be, the pressure actually will be higher. And what we do know from this relationship is that the pressure increases linearly. So what it means is, if I draw a line like this, it will be a linear relationship, and it shows that the pressure increases with the depth. Okay, so as the pressure increases with the depth, so the force actually also increases on the surface as we go down in the fluid. Okay, so and also if this is some sort of a wall, so it will have some width. Okay, so again, so this is your wall, and all of this is the fluid. Okay, so let's actually look at what our resultant force would be. The resultant force will be acting in this direction. Of course, our pressure is acting in this way, so our resultant force will also be in this way, but we don't know the location of that. But yeah, so before I actually find the resultant force, let me also remind you that on a fluid there are, okay, so on a fluid surface you also have the atmospheric pressure. Okay, so in reality, if this is your wall, you will have this atmospheric pressure, and then you have this hydrostatic pressure. But in this problem, I am not including the atmospheric pressure. The reason being, because if you have a wall over here, you also have the atmospheric pressure on the other side. So this atmospheric pressure cancels out the atmospheric pressure over here, so these two cancel out, and you're only left with the hydrostatic pressure or hydrostatic forces. So that's why I'm neglecting the atmospheric pressure. But later on in this lecture, I will look at the possibility if you have a pressurized fluid where you have a gauge pressure, so then we will have to include this this zone. Again, the gauge pressure will be contributing to some force on the surface. So if I only have this hydrostatic force, so the resultant force actually will be P times dA, where dA is this, if I take this element to be dA, and if I integrate this over the whole surface, that will be the total area. So the pressure times the area gives me the force, and I do know how the pressure is changing. The pressure is changing as rho g y dA, and I do know that the density and the acceleration due to gravity, those are constant in a liquid, so I can take those out from the integration. So we are left with y dA, which is the resultant force, and this quantity over here, which is y dA, is also known as the first moment of area. So this is our first moment of area, and it is equals to yCA, where yC is the centroid, the centroid of the geometry times the area. So the resultant force actually is rho g yCA. So this is the magnitude of the resultant force, and the centroid of the geometry is, so this is the surface that we are looking at. So if I'm looking at it from this side view, so if we have this as a rectangular shape, so this is YC. So the distance from the top of the liquid or the liquid surface to the center of this geometry is yc, and that will be the force exerted by the fluid. What we don't know at this point where that force will be located, but just to tell you that so it will be below this yc because the load is linearly increasing. So if this is where you have y of c, so the force will actually be somewhere below that, and people call it y of p or y of r, which is also known as the center of pressure. So that's where the force will be acting, but we don't know what this yr would be. We don't know what this yr is right now, but we can calculate that. And let me just draw this picture again. This is how the pressure is increasing, and I'm calling this point to be O. And we have found out this f of r, which is rho g y c a. And if I want to find where this force is acting, I need to take the moment. So take moment about O. So I'm going to take the moment about O. So alright, so that will actually be f of r times y of r. So moment about O is equals to so this side is y, so where this force is acting. So I have pda, and this also multiplies with this y, the location of that resultant force would where that is. So this is equals to y rho g y dA f of r y of r, and then we have y square. I can take this rho and g out of the integration, and then we have y square dA f r y r. And if you notice, this quantity y square dA is known as the second moment of area. Okay, so this is second moment of area, and it is represented with Ixx0 or Ixxo. The reason we have this O over here, because this is the second moment of area with respect to this point O. But we will use the parallel axis theorem to basically find the second moment of area about the centroid, which is this point C. So for now it is f of r y of r is equals to rho g I xx0, and then I'm going to use the parallel axis theorem to basically move this second moment of area from point O to point C, and I can write this as Ixx0 is equals to Ixxc plus yc square a. Okay, so I'm going to substitute this over here, and we also have this f of r that I showed you earlier, so I can write this whole thing together. So y of r, which is the location of this resultant force, is equals to rho g I xxc plus yc square a divided by rho g y ca. So this cancels out with this, and we are left with y of r is equals to Ixxc divided by yca plus yc. Okay, so that's where the resultant force would be acting. And if you notice, this is the distance to the centroid, which is yc, and this quantity will always be a positive number, so you can see that the resultant force will be below this yc, so it will be below this the centroid. Alright, so this is the case when you have a like a full wall, okay, but what if you have a case where you have some wall and then you have a gate or like some plate, and then you are trying to find the pressure on this gate. Okay, so we still have this pressure linearly increasing, and I can look at from this side. This could be a circular one, or it could be a rectangular gate, or it could be a square gate, but just for convenience I'm making this as a square or rectangular shape. So the center of this will be the centroid, okay, and the distance and this point is O, and so this distance from here to here is y of c. So this point, which will be same line, this distance is y of c. So the distance from the surface to the centroid is represented by yc, and I can find the resultant force. It will be, and the relationships are like similar. We still have to, so pda, we can take this area as dA. I integrate this over the entire surface, so f of r is equals to rho gy dA, and I can take the rho and g out of the integral, and then we have y dA. So this y dA, as I showed you earlier, this is the first moment of area, which is equals to y dA is equals to yc times the area, which this is the centroid, this distance, and if this is my y-axis, so this is the distance of the centroid. So I can write this resultant force is equals to rho g yca. So our resultant force is exactly the same way we computed earlier, and now let's try to find where this resultant force is acting. Okay, so I have to find where this resultant force is acting, and I'm calling that distance to be yr. In order to find the yr, we have to take the moment about this point O. So take moment about point O. Okay, so when I take the moment about point O, f of r, y of r is equals to y pda, as we did earlier. So f of r, y of r is equals to y rho g y dA. And if you notice, this is the same expression that we obtained earlier, so I'm just gonna show you and then I will write the result. So y of r is simply equals to ixxc over yca plus yc. So this will tell us where this resultant force is acting, and this is important that this distance yc is this the centroid of this geometry, okay, which is in this case is the gate. Alright, so at this point I'm going to do an example. Alright, so let me just first show you an example. So what it says is a tank contains oil which has a specific gravity of 0.9 and has a square 0.6 by 0.6 meter plate bolted on its side. Find the magnitude and the location of the resultant force on the attached plate. So if I am looking at a container or a tank that looks something like this, so it can be and then it's filled with liquid which has a specific gravity of 0.9, and the height of that is, so over here up until this distance, and somewhere over here you have this gate which is 0.6 meters by 0.6 meters. And what we want to find out is what will be the forces exerted on this one over here. So if I am looking at it from the side view, so if this is my gate or like the plate, I have some liquid on the top, so this is the wall, you have something on the bottom also. So the pressure distribution will look something like this. Okay, and then I'm calling this point again O, and this distance, what we do have is y of c, because it's the centroid of this geometry. So the resultant force, as we talked about earlier, so the resultant force is simply rho g yca. So that will give me the resultant force. And I mean, so this is one way, or I can write this as gamma times rho yc times the area. And so the horizontal or this resultant force is actually equals to 0.9, which is the specific gravity, times the specific weight, 10 raised to power 3 Newton per meter cube. And the units have to be consistent, so which is the YC. You have liquid on the top, which is 2 meters, and then this thing is 0.3 meters, so that's why the distance of the centroid from this point O is 2.3 meters. And then you have the cross-sectional area of this plate, which is 0.6 times 0.6, which is 0.36 meters square. So your resultant force is equals to 7.31 into 10 raised to power 3 newtons. So you have the resultant force, and where this resultant force will be acting, we also derived that relationship. So that relationship was y of r is equals to I xxc divided by yca plus yc. So looking at this expression, we have this yc, which is 2.3. We also have this yc here, which is 2.3. The cross section, the area of the plate is 0.36 meters square. The only missing quantity is this Ixxc, which is the second moment of area for this plate. So Ixxc for a square shape is basically equals to A4 by 12. So in this case it is 0.64 divided by 12. So that gives me 0.0108 meters to the power 4. Okay, so 0.0108 meter to the power 4, and I will put those numbers in here. So that is 0.0108 meter to the power 4 divided by yc, which is 2.3 meters, and then I also have the area 0.36 meters square plus yc, which is 2.3 meters. And as you can see from here that this will be a positive number, so yr won't be acting at the centroid but slightly below this. And once I add those numbers together, so this is 2.313 meters. So from this point O, because we were taking the moment about point O to basically obtain this relationship as I showed you earlier when we were deriving that, so this distance is from point O, and the distance from here to here is 2.313 meters, which is more than 2.3 meters, and that's the distance for these from the centroid to that point O. Alright, so this is when you don't have any pressure, external pressure acting on the fluid. But what if you have some external pressure acting on the fluid, and I'm representing that with the gauge pressure? Okay, so in this case we have a fluid. Okay, so and here is a gate, and on this fluid we have some external gauge pressure. Okay, so and we also have the hydrostatic pressure. So the pressure distribution for this will look something like this. I mean, so you have this gate over here. So the gauge pressure, it will be evenly distributed, and that's how it's going to look like. And then after that you have this hydrostatic pressure, which is going to linearly change. Okay, so I mean, again, I can represent it over here. So you have a gauge pressure and so on. So let's try to find out what the resultant force for this case would be. You have PdA, you still have the you have to pressure times the area will give you the force, but now the pressure has two contributions. One is coming from the gauge pressure and the other one is coming from the hydrostatic pressure, so we need to include both of those. So P of gauge plus rho gy times dA, and then you have P of gauge times the dA integral plus rho gy dA integral. Okay, so rho gy dA, yes. And I'm calling this one to be FR1 just because you have a contribution from this from the gauge pressure, and you also have a contribution from the hydrostatic forces. So I'm calling this one as FR2. So FR1 is simply, we have this quantity, I can integrate this, and that will give me P gauge times the area, and FR2 is something we have already looked before, so I can take this rho and G out, and this will be Y dA. So okay, so rho G Y dA, and this Y dA is first moment of area, and I can write this as rho G Y CA. So this is the force FR1, this is force FR2, so the resultant force will actually be FR1 plus FR2, which so you add those up and you basically have that resultant force. Alright, so now we're going to look at where these forces are acting. So we will take the moment about point O. So if I am calling this point to be O, or in this case if I call this point to be O, and I will see the moment about point O. Okay, so take moment about O. Alright, so in this case, let me also present it over here. Alright, so we have a gate here somewhere, and this is the shape, and that's where the distance from the centroid is. So this is YC, and so on, and this is this, and then you have a gauge pressure, and okay, so let's take the moment about O. So we have Y of R, F of R is equals to Y PdA. Okay, so this side is the Y. So now we have Y times P of gauge times dA plus Y rho gy dA, and this is Y of R, F of R. Alright, so I can take the P of gauge out of the equation because this is a constant. So Y dA plus rho g y square dA, and this is Y of R, F of R. Alright, so here is an important point, that if you would notice, this is the first moment of area, this is the second moment of area. So for the gauge pressure, the contribution that's coming from the gauge, so this pressure, if you notice this quantity, this pressure is acting at the centroid of this geometry or this plate. So that's where the gauge force is acting. So I can replace it with P gauge times YCA. So P gauge times the area is the force, and this force is acting at the centroid of this geometry. Okay, so which is the centroid of this, plus rho G I XXO, and this is the second moment of area about point O, and we have Y of R, F of R. Okay, so I will be basically using the parallel axis theorem to move this to the centroid of this geometry. So I'm going to write this Y of R, F of R, P gauge, area YC plus rho G IXXC plus YC square A. And then in order to find this Y of R, we have the whole relationship, and I will simply divide this thing. And if you will notice, like most of these quantities we can easily compute, and the gauge pressure and everything will be given to us, and then we have F of R. So this tells us where the location of that resultant force would be. Alright, so let me actually do an example, and in fact which is very similar to the example that I did before, except for now the fluid is pressurized. So What it says is a pressurized tank contains oil, a specific gravity of this much, has a square 0.6 by 0.6 meter plate bolted on its side. Find magnitude and location of the resultant force on the attached plate. So let me draw a picture. Because we have some fluid, and on top of that fluid we have this external pressure, the gauge pressure. So let's suppose if this is the tank that we are dealing with, and over here we have this gauge. I did not specify what the gauge pressure and everything would be in here, but let me give the numbers here. So P gauge, I am giving a 50 kilopascals. So 50 kilopascals is the gauge pressure, and like we had in the previous case, we have the fluid. So until 2 meters we still have the fluid, and after that we have the plate, or the rectangular plate, which has the dimensions of 0.6 meters times the 0.6 meters. And what we want to find is magnitude and the location of the resultant force on the attached plate. So as I look at from the side view, you have this plate, and then you have this contribution coming from the gauge pressure, and then you have this hydrostatic pressure. And as I was deriving this, I said that the gauge pressure is acting at the centroid of this geometry. Alright, so and then we have to so first of all we have to find the two forces, the FR1, FR2, which will give us the total force. So let's try to compute this FR1, which will be, so this is FR1, this will be somewhere over here is FR2. So FR1 is simply P gauge times the area. So P gauge in this case is 50 kilopascals, so 50 into 10 raised to power 3 Newton meter square times the area, which is 0.36 meters square. And when I compute that, it gives me an 18 into 10 raised to power 3 newtons force. So this is the force FR1, and in a similar way, because not in a similar way because this is a hydrostatic force, so FR2, something like this we have obtained earlier in the previous example. So gamma YCA is equals to 0.9 times 9.81 into 10 raised to power 3 Newton per meter cube times the distance of the from this point, which I'm calling point O again. Distance from here to the centroid of this is 2.3 meters, and then we have the cross-sectional area, which is 0.36 meter square. So when I add up all of these, this gives me 7.31 into 10 raised to power 3 newtons. So I have FR1, which will be acting, which is representing this pressure, FR2, which is representing this pressure. So the total pressure acting on this, the total force acting on this is FR1 plus FR2. So I add these two up, and then this gives me 25.31 into 10 raised to power 3 newtons. So this is my resultant force. So to find the magnitude and the location of the resultant force, so we found the magnitude of the resultant force, FR1 plus FR2. So now let's try to find what the resultant force, so where this resultant force would be acting. So in order to find the resultant force, we will have to, okay, so we have the gauge pressure and everything. So this point is O, so take moment about O, and F of R, Y of R is equals to P gauge, and this is the same relationship that we derived earlier. I'm using that. So P gauge times area times the distance to the centroid. So this is my gate. So looking at it from here, so this distance from here to here is Y of C. So and then we have rho G I x x C. So this is the second moment of area about the centroid, Y C square A. And now I have this quantity we computed in the on the previous page, or like the previous right, so I mean, yeah, we computed that. So and then this multiplied with 2.3 meters, and then we also have this, which is 0.9 times 9.81 into 10 raised to power 3 Newton meter cube, times Ixxc, which is the second moment of area. And for a square shape like that, the second moment of area basically is Ixxc is equals to A4 by 12, and in this case it's 0.64 by 12, and that gives us 0.0108 meter to the power 4. And then I mean, so this everything is inside the bracket, plus I have 2.3 meters square times 0.36 meters square. Okay, and then close this bracket, and once I put everything together, this gives me 41.4 into 10 raised to power 3 Newton meter, plus 16.9 into 10 raised to power 3 Newton meter. And then I also have this 25.31 into 10 raised to power 3 Newton meter, actually Newton. And then we have this y of r. Alright, so y of r is basically equals to 2.3038. So in other words, when I look at it, this plate, so the liquid started out from here, so this distance was 2, the centroid distance was 0.3, so altogether this y of c was 2.3. so our resultant force is acting at a distance of, so slightly below the centroid, which is 2.3038. so that's where the resultant force is acting, which is below the centroid. Alright, so that's pretty much what I wanted to do for this. In the next video I will show you how to find the loads and the resultant forces, and also the moments about an inclined plane or curved surfaces. So see you then.